Hey there, science fans! Welcome to another exciting journey into the world of science, where we explore the building blocks of our universe. Today, we're diving into the fascinating world of atoms. Atoms are the tiny, fundamental units that make up everything around us, from the air we breathe to the Lego bricks we love. Imagine a tiny Lego spaceship orbiting a Lego planet. This visual can help us understand how electrons move around the nucleus of an atom. That spaceship follows a specific path, right? It moves in a predictable orbit, much like how we once thought electrons orbited the nucleus. In the quantum world, electrons behave similarly, but instead of fixed paths, they reside in regions called orbitals. These orbitals are like clouds where electrons are most likely to be found. These orbitals surround the atom's nucleus, much like our Lego spaceship circles its planet. However, unlike the spaceship, electrons don't follow a single clear path. But how do these tiny electrons orbit the nucleus? What keeps them in these orbital regions instead of flying off into space? Let's unlock this mystery. Years ago, scientists pictured atoms like mini solar systems, with electrons orbiting the nucleus like planets around the sun. This was known as the Bohr model, named after the scientist Niels Bohr. It was a revolutionary idea at the time and helped us understand atomic structure better. The Bohr model depicted electrons in fixed orbits, much like planets in our solar system. However, it had limitations and couldn't fully explain the behavior of electrons. Especially when it came to their energy levels and the way they interacted with light. Enter the quantum mechanical model, a more accurate picture of the atom. This model uses complex mathematics to describe the behavior of electrons. This model introduces the concept of orbitals. Orbitals are not fixed paths, but rather regions where electrons are most likely to be found. Orbitals aren't fixed paths, but rather regions where we're most likely to find electrons. Think of it like this: instead of our Lego spaceship following a precise route, it zips around the planet in a blur, with some areas more frequented than others. This means that electrons are more likely to be found in certain areas within an orbital, just like our Lego spaceship might spend more time in some parts of its orbit than others. Now, how do we keep track of these speedy electrons within their orbitals? Scientists use a set of numbers to describe the properties of these orbitals. That's where quantum numbers come in. These numbers act like special address labels for electrons, telling us their energy level, shape, orientation, and even spin. These quantum numbers are essential for understanding the complex behavior of electrons in atoms. They help us predict where an electron is likely to be and how it will interact with other particles. We have four main quantum numbers: N, L, ML, and Ms. Let's explore each one. These numbers give us a detailed map of the electron's position and behavior within an atom. First up is the principal quantum number, represented by the letter N. This number is fundamental in understanding the structure of atoms and how electrons are arranged within them. Think of it as the energy level of an electron, like floors in a building. Each floor represents a different energy level where electrons can reside. The higher the N value, the higher the energy level, and the farther the electron is from the nucleus. This means that electrons in higher energy levels have more energy and are less tightly bound to the nucleus. Imagine our Lego spaceship orbiting our Lego planet. The spaceship's distance from the planet represents the electron's distance from the nucleus. If the spaceship represents an electron, the farther it is from the planet nucleus, the higher its energy level. This analogy helps us visualize how electrons occupy different energy levels. We can visualize these energy levels as Lego shells surrounding the nucleus. Each shell represents a different principal quantum number, N. The first shell, closest to the nucleus, has an N value of 1. This is the lowest energy level and can hold the least number of electrons. The next shell out has an N value of 2, and so on. As N increases, the shells get larger and can hold more electrons. Each shell can hold a specific number of electrons. This capacity is determined by the formula seconds squared, where N is the principal quantum number. For example, the first shell can hold up to 2 electrons as it has an N value of 1, while the second shell can hold up to 8 electrons, corresponding to an N value of 2. This pattern continues for higher energy levels. Next, we have the angular momentum quantum number, often denoted as L. This quantum number is crucial because it determines the shape of an electron's orbital, which is essential in understanding how atoms bond and interact. Remember those different Lego brick shapes we talked about earlier? Each shape represents a different type of orbital. Well, L dictates what those orbital shapes look like. It's like having a blueprint for how each Lego piece should be shaped. We assign specific letters to different L values. S for L equals 0, P for L equals 1, D for L equals 2, and F for L equals 3. These letters help us easily identify the shape of the orbitals. Each letter represents a different orbital shape, which is fundamental in the structure of atoms. The S orbital is spherical, like a Lego ball. It's the simplest shape and is found in all energy levels. The P orbital resembles a dumbbell, like two Lego bricks stuck together. These orbitals are found starting from the second energy level. The D and F orbitals have more complex shapes. The D orbitals start appearing in the third energy level, while the F orbitals are found in the fourth and higher levels. Orbitals with the same principal quantum number and are grouped into subshells. These subshells help us understand the distribution of electrons within an atom. For example, the second energy level, where n equals 2, has two subshells, 2s and 2p. This means it can hold different types of orbitals. The 2s subshell has one spherical s orbital, while the 2p subshell has three dumbbell-shaped p orbitals. This arrangement is crucial for the chemical properties of elements. Now, let's talk about orientation. The magnetic quantum number, ml, describes the orientation of an orbital in three-dimensional space. Picture our Lego p orbitals shaped like dumbbells. We can position them along the x, y, or z axis, right? That's what ml does. The ml value can be any integer from -L to +L, including 0. For example, a p orbital, L equals 1, can have ml values of -1, 0, and +1, representing its three possible orientations. This means each subshell can hold a specific number of orbitals. The s subshell has one orbital, the p subshell has 3, the d subshell has 5, and so on. Section 5. Spin quantum number ms. Spinning electrons. Lastly, we have the spin quantum number, ms. This one's a bit trickier to visualize, but imagine our Lego bricks spinning. Electrons don't actually spin like tops, but they behave as if they do. This spin creates a tiny magnetic field. The spin quantum number has only two possible values, +1/2 and -1/2. These values represent the two possible spin states of an electron, often called spin up and spin down. You can think of it like our Lego bricks spinning clockwise or counterclockwise. Section 6. Quantum numbers and the periodic table building blocks of matter. Now, how do these quantum numbers relate to the periodic table? The periodic table is organized by increasing atomic number, which is the number of protons in an atom's nucleus. But the arrangement of elements also reflects the filling of electron orbitals, guided by our quantum numbers. As we move across a row, or period, in the periodic table, we're filling electron orbitals according to the Aufbau principle, which states that electrons fill lower energy levels first. The periodic table shape reflects the different types of orbitals and their energy levels. For example, the first two columns represent the filling of the s orbitals, while the last 6 columns represent the filling of the p orbitals. Section 7. Beyond the basics. A glimpse into advanced concepts. We've covered the basics of quantum numbers, but there's so much more to explore. For example, did you know that orbitals aren't fixed paths, but rather probability clouds? It's like our Lego spaceship moving so fast that it becomes a blur. We can't pinpoint its exact location, but we know the areas it's most likely to be found. We can visualize these probability clouds using something called electron density maps. These maps use shading to show the likelihood of finding an electron in a particular region. The denser the shading, the higher the probability. Section 8. Conclusion. Unlocking the secrets of the quantum world. Congratulations, science explorers! We've journeyed into the heart of the atom and uncovered the secrets of quantum numbers. These numbers, acting like address labels for electrons, help us understand the structure of atoms and the arrangement of elements in the periodic table. But our quantum adventure doesn't end here. The world of quantum mechanics is full of fascinating phenomena waiting to be discovered. So keep that curiosity alive, keep asking questions, and keep exploring the incredible universe we live in.